Welcome to your next lesson on the electric circuits topic. Today we're going to take a look at resistance. This is the first part out of two lessons where we're going to be taking a look at resistance. Your key learning for today is state the effect of varying resistance on current, apply knowledge of charge flow to a model for current and resistance, analyze a model for resistance in a wire, and hypothesize why we get sparks. Before we move on to resistance, let's take a look at some recap questions. Linking back through this topic, answer the following. What is the symbol for potential difference? What is the unit for charge? What is the symbol for charge? What is the equation linking charge, potential difference, and energy? And finally, what is the equation that links current, time, and charge? Pause the video now, have a go at these questions, and when you're ready for the answers, press play. So let's see how you've done. Question 1. What is the symbol for potential difference? It's a capital V. Question 2. What is the unit for charge? It is the coulomb, or a capital C. What is the symbol for charge? It's the capital Q. What is the equation linking charge, potential difference, and energy? It is E equals QV from last lesson. And finally, what is the equation that links current, time, and charge? This is from 2 lessons ago. It is Q equals IT, or charge equals current times time. Take a look at this image. What does this image tell you about the relationship between current, potential difference, and resistance? Written on the little cartoon characters are the units for each of those things. So the ohm is the unit for resistance. This will be the first time that you've come across the word ohm. We'll revisit ohm when we take a look at the equation next lesson. The volt is the unit for potential difference, and the amp is the unit for current. So, how are they all related? Try and answer that question. Pause the video now. Try and use the words resistance, potential difference, and current in your answer. When you're ready to move on, press play. So let's take a look. Well, the first thing that you'll notice is that the volt is pushing the amp. In other words, the potential difference pushes the current through the wire. Without the potential difference, there would be no current. If you increase the potential difference, the current would increase. The next thing, which is new to you, is that the resistance tries to stop that current from flowing. Now let's take a look at resistance a little bit more closely. What is resistance? The word resistance just means to try and stop something. So you could apply the word resistance to, let's say, you're resisting the temptation to have that 14th slice of pepperoni pizza at the Pizza Hut buffet. Another application of the word resistance is in this picture. Those horrible people have attached a parachute to that poor lady while she wasn't looking, to make her feel bad about her running. No, not really. She's got some kind of a resistance parachute on to help her with her training to build strength. The parachute is there to resist her flow. In electric circuits, the resistance does a very similar thing. Now we're going to take a look at using a model. We often use models in science, especially when we're talking about things that are very difficult for us to picture, such as charges moving through a wire. So instead, we use things like marbles, which are very easy to picture. So, watch the demonstration, and I am going to give you some questions to answer after the demonstration. So make sure that you pay attention to what all the parts of the model represent. Let's go through the setup for this model. Here we have a corkboard which has been raised at an angle to the table surface, making it into a ramp. Here is where we place our marbles, and I've placed some pins in the board in front of the marbles between the top and the bottom of the ramp. So what does all this represent? The surface of the corkboard represents the inside of a wire. The marbles, which will be rolling down the ramp, represent the charges. You can think of them as individual electrons if you like. The height of the marble represents the potential difference. If you remember from last lesson, we saw that the potential difference is the amount of energy that is given to a unit of charge between 2 points. Here, our model uses the gravitational potential energy store to move the marble from the top to the bottom of the ramp, to represent the energy provided by the battery to move the charge through a piece of wire. We could use our model to change the potential difference. If you want to represent a small potential difference, this would mean giving the marble less energy, which we get from the gravitational potential store. And as you know, the higher something is, the more gravitational potential energy it has. So we would raise our corkboard through a small angle. Likewise, if you wanted to represent a larger potential difference, we could use a larger angle. For today's demonstration, we will be keeping the potential difference the same, so we will not be changing the angle. Next, we have the rate at which the marbles will roll down the ramp, which represents the rate of flow of charge, or as we know from lesson 3, this is more commonly called current. We could take this model a little further without the pins. Looking again at the diagrams below, what would happen to the rate at which the marble rolled down the ramp in the low potential difference diagram? We would get the marble slowly rolling down the ramp, which would represent a slow rate of flow of charge, or a low current. The marble would roll down the ramp much more quickly for the high potential difference ramp, representing a high rate of flow of charge, or a high current. Finally, we get to the pins. The pins have been placed in the path of the marbles to resist the motion of the marble. So the pins represent the resistance in our model. The more pins we have, the more resistance we have. So let's take a look at the physical setup that I'm going to use for this demonstration. If we take a look at the top, this is where I'm going to keep my marbles, held back by a ruler. I'm using a ruler so I can release all the marbles all in one go. On the left-hand side, you can see a low resistance wire represented by fewer pins, and on the right, more pins means higher resistance. See if you can work out which side the marbles travel faster. That was a bit tricky to see, so let's take a look at that again, but this time in slow motion. Remember, the left-hand side is low resistance, the right-hand side is high resistance. In which wire is the current the highest? Hopefully you can see there that the wire on the left-hand side, the low resistance wire, allows for a higher current. So let's try measuring that current. For this, we're going to need to use a stopwatch. And we are going to count every marble as being equal to 1 coulomb of charge. And we're going to count how many marbles passed beyond this line in the first second. And that'll give us how many coulombs per second past that point. This will give us a value in amps for the low resistance and the high resistance wire. Remember, there are 6 marbles on each side. Let's pause it at 1 second. On the left, 5 coulombs have passed that line in 1 second, that's 5 amps. And on the right, 3 coulombs have passed in 1 second, that is 3 amps. Now that you've seen the model in action, I would like you to test your understanding of the resistance model. Complete the following. Number 1, in the model, explain what was represented by A, the marbles, B, the tilt of the ramp, C, the rate that the marbles rolled down the ramp, and D, the number of pins. Part 2. Using the model in your answer, explain what the effect of resistance is on the current if we keep the potential difference the same. To strengthen your answer on that one, you might want to use some of the numbers. And finally, for number 3, which is your challenge question, what are the limitations of this model? In this case, the word limitations, I'm referring to, are there any aspects of the model that actually, they're not really making sense as far as current, charge, potential difference and resistance are concerned? It's not a perfect model. Why not? Pause the video now, and when you're ready to move on, press play. So let's take a look at some of your answers. Number 1. In the model, explain what was represented by A, the marbles. The marbles represented charge. B, the tilt of the ramp. The tilt of the ramp represented giving those charges a potential difference. C, the rate that the marbles rolled down the ramp. Well, how fast the marbles rolled down the ramp represented the rate of flow of charge, or the current. And finally, the number of pins represented the resistance. 2. Using the model in your answer, explain what the effect of resistance is on current if we keep the potential difference the same. So you could have written something like this. Increasing the resistance decreased the current. This could be seen in the model as the increased number of pins represented more resistance to the flow of charge, which was represented by the marbles. The high resistance model only allowed a current of 3 amps to flow, whereas the low resistance model allowed 5 amps to flow. Your wording may be different, but as long as it's along the same lines, well done. Now moving on to part 3, which is your challenge question. What are the limitations of the model? Well, you could have thought of anything, really. Here are a few thoughts of mine. Perhaps you've got something different. It doesn't account for electron-electron repulsion. In other words, those marbles, if they were representing negative charges, would be repelled away from each other. But instead they could clatter against each other on the way down the ramp, which wasn't representative of what electrons do. The model also suggests that density is the main cause of resistance. This isn't actually the case. It's a good model for resistance, but the fact that there are more pins doesn't necessarily mean that there are more particles in something that resists charge. And finally, there are a small number of charge carriers. In other words, there were very few marbles. Could we have improved the model by having hundreds of them stacked up above the ruler? There are many other possibilities. Any model in science is not perfect, but it gives us a bit of an idea, a bit of a way of thinking about things which helps us to understand them better and to help us picture things that we otherwise wouldn't be able to picture. Finally, I would like you to think back to your Sparks sheet. So, during the fields lesson, I gave you this task. Why do we get sparks? You should have added some notes on for fields, current, potential difference, and now I would like you to add the final piece onto your hypothesis as to why we get sparks, using what you've learned today about resistance. You may want to revisit this question again at the end of part 2 of the resistance subject. Thank you for watching. I hope you enjoyed it.